Friends, today we are going to discuss the applications of theory of relativity. The first application is Lorentz Fitzgerald contraction. In this contraction, according to Einstein, the length of the rod is vary with the velocity. That is, it depends on the velocity of the light. In this article, we are going to study the velocity of the rod is depends on their velocity. So, when the rod is in motion or any object is in motion, its length decreases. This is the conclusion of this article. So, in this article, we first consider a rod in a frame S and S dash, and these two frames are coincide with each other. Here, initially the frame S is stationary while frame S dash is moving. At time t equal to 0, both the frame S and S dash are superimposed on each other and coincide with each other. When time start, the moving frame S dash start moving with velocity v along the positive direction of x-axis. The rod AB also moves with the same velocity with the velocity of S dash frame. Let AB is the rod whose length is L according to the observer in S frame. Let the coordinates of the rod for stationary frame are according to stationary frame or observer in the S frame. The coordinates of the two rods are x1, y1, z1, t1, and according to S dash frame or S dash observer, the coordinates are x1 dash, y1 dash, z1 dash, and t1 dash. These are the coordinates according to S dash frame. According to the Lorentz contraction, the coordinates, the x coordinate of the rods are given by x1 is equal to k into x1 is equal to x dash or x1 dash plus vt dash divided by under root 1 minus v square upon c square, and another coordinate x2 is equal to x2 dash plus vt dash divided by under root 1 minus v square upon c square. These are the coordinates of the rod according to stationary frame of reference or observatory S frame. So, what is the length of the rod? The length of the rod will become x2 minus x1, that is the difference of two coordinates, and is equal to, let it is L, and this L is known as the apparent length of the rod. Apparent length of the rod. Similarly, the another coordinates x1 dash and x2 dash, these are the coordinates of the same rod according to observer in S dash frame. Therefore, according to observer in S dash frame, the length of the rod become x2 dash minus x1 dash is equal to L0. This L0 is known as proper length of the rod. Okay, now let us consider the two equations according to Lorentz direct transformation relations, that is x1 dash is equal to x1 plus v t dash divided by under root 1 minus v square upon c square, and another coordinate is x2 dash is equal to x2 dash plus vt dash divided by under root 1 minus v square upon c square. So taking the difference of these two coordinates, we get x2 dash is x2 dash plus vt dash upon under root 1 minus v square upon c square minus x1 dash is x1 dash plus vt dash divided by under root 1 minus v square upon c square and is equal to x2 dash minus x1 dash. I am sorry, this is not here dash, so I can write x2 dash minus x1 dash is equal to x2 minus x1 divided by under root 1 minus v square upon c square. After solving this, we get x2 dash minus x1 dash is equal to L0 is equal to this x2 minus x1 is L divided by under root 1 minus v square upon c square. So I can write here L is equal to L0 into under root 1 minus v square upon c square. So the next equation, this equation reduces to when v is equal to c, the above equation reduces to L is equal to L0 in bracket 1 minus c square upon c square. So L is equal to L0 into in bracket 1 minus 1 and L is equal to L0 into 0. So L is equal to 0. From this equation it is clear that when the rod moves with the velocity of the light, its length decreases and it is almost 0 when the velocity approaches to the velocity of light. Thank you.